Hi, my name is Daniel Mitropolsky, and welcome to the ITCS talk on total functions in the polynomial hierarchy. This is joint work with my advisor, Christos Papadimitriou at Columbia, Bobby Kleinberg at Cornell, and Oliver Corton at Columbia. So here is an overview of our work at a very high level. This talk is about function problems, not decision problems. And very occasionally, we might use a decision complexity class when we mean a function class. I'll point that out if that happens. So specifically, we're interested, for instance, in FNP and not decisional NP. What is FNP? As a quick reminder, the complete problem for FNP is the SAT search problem. It is given a satisfiable formula, find a satisfying assignment. This can, of course, be verified with a polynomial time machine. Of course, in this relation, not every formula participates in the relation. Not all of them are satisfiable. So this leads to the definition of TFNP, or total FNP. These are problems in FNP that are total. Every instance has a solution. But we'll define this more rigorously in a second. And recall from your Introduction to Complexity course that NP generalizes to a polynomial hierarchy of sigma I and pi I complexity classes. So in our work, we essentially generalize TFNP to an analogous hierarchy of classes, which we call TF sigma I. And we identify natural problems in these classes, as one does in TFNP research, and corresponding subclasses in this hierarchy. So without further ado, let's begin. So let's define TFNP. A relation Rxy is total if for every x there is a y, such that xy is in the relation. In other words, for every input, there is some solution or some y in the relation. And TFNP can be defined as those relations in FNP which are total. But here is a more technical definition, which if you'd like, you can stop and look at. A relation is in TFNP if it's polynomial. So the y's are polynomial. There's a fixed polynomial in the length of x. The relation is total. And there exists a polynomial time machine such that xy is in the relation if the machine accepts xy. Great. So a little bit about TFNP. Probably TFNP has no complete problems, unlike FNP, which, as we've discussed, has the complete problem of search SAT. But TFNP does have a variety of interesting problems where a solution is guaranteed. In other words, the problem is total. This has to be the case for it to be in TFNP. But we do not know how to compute this solution in polynomial time. So some sort of argument, some sort of non-constructive argument guarantees that a solution exists for every x. And then evidence for intractability of a specific search problem can be obtained by showing completeness of that search problem for one of these subclasses in TFNP. So these subclasses are defined by reduction to some problem, and what they're really defined by is that they're grouping problems in TFNP by a shared combinatorial principle, which is used in the proof of totality. Right? The same principle guarantees existence of a solution. And this underlies the definition of all of the TFNP subclasses that you may have seen before: PPP, PPA, PLS, and so on. So let me tell you about one of these classes in particular and the very simple combinatorial argument which gives rise to it. This example is the class PPP. So consider the following simple argument. Given a mapping which has fewer outputs than it has inputs, there has to be a collision in the output space. And this is guaranteed by the set theoretic pigeonhole principle. So let's translate this to a concrete computational problem. We define the pigeonhole search problem. Given a circuit which maps n-bit strings to n-bit strings, either find an x that is the preimage of the 0 string, or find a collision. And this problem is total. A solution is guaranteed to exist because if there is no preimage of 0, the output space is smaller than the input space, so there must be a collision by the pigeonhole principle. This is a very simple problem to define, but of course, the solution is guaranteed by this set theoretic argument, and it's unclear how looking at a circuit, which implicitly represents this mapping, how to find this collision, or a preimage of 0 for that matter. So we define the class PPP, which stands for Polynomial Pigeonhole Principle. The first P doesn't stand for Papadimitriou, contrary to popular belief, as those relations in TFNP which are polynomial time reducible to the pigeonhole problem. But now consider this simple combinatorial argument, the empty pigeonhole principle. This time, given a mapping with more outputs than inputs, by the same logic, there exists an empty pigeonhole. There exists some output which isn't mapped to by any input. And so analogously, we can define a computational problem, the empty problem. This time we're given a circuit mapping 2 to the n minus 1 inputs to 2 to the n outputs. Concretely, we can simply remove the 0 string as a possible input. All right, it's not considered. And the goal is to find a y such that there is no x that maps to y under this circuit. Now, at very first glance, this seems somewhat similar to the pigeonhole problem. And one can ask, is it in PPP? Is it PPP complete? But when you think about it, even briefly, you'll see, no, this is somehow different, because checking a solution requires looking at all the pigeons in the input space. So there seems to be some sort of quantifier at play. You have to look at all possible inputs to check that that y as an empty pigeonhole. So this leads to the definition of TF sigma 2. All right, TF sigma 2 can be thought of as total problems in functional sigma 2. But here's a concrete definition. A relation Rxy is in TF sigma 2 if it's a polynomial relation, if it is total. And this time there exists a verifying machine M and polynomial P such that xy is in the relation if for all z of this polynomial length, M xyz accepts. So in other words, the sigma 2 machine accepts. And analogously, we can define an entire hierarchy of total search classes, the TF sigma I, which are total relations in functional sigma I. And if you want, you can take a second to pause and look at these definitions. But they correspond to definitions of the polynomial hierarchy in decisional problems. Great. So now let's get back to this empty problem we were talking about. So I'll remind you briefly of the technical definition of empty. We're given a circuit mapping 2 to the n minus 1 inputs to 2 to the n outputs, and we have to find a y such that no x maps to y. Now we can say that empty is in TF sigma 2. The verifying machine quantifies over all possible x and verifies that none of them map to y. And I'll take a moment at this point to say, and the details are spelled out in our paper, that the TF sigma I, the total hierarchy, behaves in ways you might expect. You can essentially define the TF sigma I as TFNP with a sigma I minus 1 oracle, similar to how you can define sigma I through oracles. And this, I remembered this now because one could define M as a polynomial machine with a sigma I oracle. And it checks that no x maps to y. And similarly to how we define subclasses in TFNP based off a problem which is total by some natural non-constructive argument, we define the class PEPP, which stands for Polynomial Empty Pigeonhole Principle, as all the total relations in TFNP, all total relations which are polytime reducible to the empty problem. So PEPP is some subclass of TF sigma 2. And this is a bit informal, but one should think about PEPP as search problems where the solutions are guaranteed by the union bound or the empty pigeonhole principle. But the union bound is another way to think about that. In the union bound, we are given a bunch of sets and we know the size of these sets. And we know that the sum of the sizes of these sets is less than some output space. So there must be an element in the output space which isn't in any of the input spaces. And if you translate this to some circuit search problem, you end up with the empty definition, essentially. So we will see this union bound argument reappear. And incidentally, and this is interesting, FNP is in PEPP. Now, let me explain this for a second, because this might be a bit confusing. FNP isn't even, the problems in FNP aren't total. What we described at the beginning, the search version of SAT, there are many x which don't participate in this relation, namely all x which are not satisfiable formulae. But you can extend such a relation to one where for the non-satisfiable formulas, you insert into the relation that formula with an output, such as the word unsatisfiable. Now, of course, that can't be verified by an NP machine, but it turns out that that relation is in PEPP. So that's what's meant by this. And the proof is easy. But it's interesting because this somehow says something different about PEPP from TFNP, for instance. Great. Now I will present to you several problems that we identified, which are very natural and live in TF sigma 2, and in fact live in PEPP. And I've sort of chosen the most interesting ones. So this is the remote point problem. We're given a circuit which represents a code which goes from m bit strings to n bit strings. Okay, and n is going to be larger than m. And we're also given a d such that when you take all the code words produced by C, and you take Hamming balls of size d around all of those code words, you don't cover the entire output space. And by the union bound, there must be a bit string in the output space, which is neither a code word nor in a d Hamming ball around any code word. So find a bit string which is Hamming distance d far from any code word. So this is an interesting problem, and it relates to coding theory. And at first, we asked ourselves whether this was PEPP complete, and we thought maybe this would be an interesting problem. But based on how it's defined, it's actually trivially PEPP complete. You simply take d equals 0, and then you're looking for a bit string which is different from any input. But of course, the problem remains for large d. Sorry, this should say, what about for large d? And it also is interesting to ask whether this problem is complete or what are its properties if C must be a linear code or some other restriction on C other than being an arbitrary circuit. Now, the next natural problem is matrix rigidity. So matrix rigidity. We say that a matrix, an n by n matrix M over a field F is delta rigid if it is quite far from having low rank in a certain sense. It's delta rigid if you can't modify M to have rank less than delta times n, which is much less than n, by only modifying n to the delta entries in every row of this matrix. Clearly, if you replace all the entries in the matrix with 0, it would have 0 rank, but it can't be done by only replacing n to the delta entries in each row. The existence of delta rigid matrices is guaranteed also by a very simple union bound like argument. There exists one for every n by n matrix, but there even exists one for every matrix where you filled in several of the first rows with some values. So this leads to the definition of a very natural search problem, the delta rigid matrix completion problem. Given the first log n rows of an n by n matrix over some fixed field, but let's take F2 as a simple example, find a delta rigid completion of this matrix by filling in the remaining n minus log n rows. So as I just explained to you, and you can look at the details in the paper, this is a total problem. Again, the union bound guarantees the existence of these completions. And you may ask, why are we providing the first log n rows as an input? You could define this problem without that and say simply find a delta rigid matrix of size n by n, but then this becomes a unary search problem. And this is more general, in fact, right? We're saying it's a total problem for any input to the first log n rows, we can find a delta completion of that matrix. So you can think about this, and you'll see very quickly that it is in TF sigma 2, because the verifying machine can simply try all modifications to this matrix. In each row, you can make at most n to the power of delta of them. So we simply try n choose n to the delta modifications in each row. And that can be quantified over with a polynomial string. And in fact, a very simple union bound-like argument shows that this problem is in PPP. And you can look at the details. And so here's the next very natural problem, the third one. And it has to do with, in a sense, this problem is related to one of the fundamental goals in complexity theory, which is to find a Boolean function and variables which require super polynomial circuits. In an early proof by Shannon, which also uses a union bound-like argument, we know that almost all Boolean functions need large circuits. They need circuits larger than 2 to the power of some constant times n divided by log n size circuits. And of course, we don't know any such explicit, simple natural function. And this is one of the fundamental goals of complexity theory, to separate, say, P poly from P even. So we are going to come up with a corresponding search problem. So given a bit string x of length m, this is important, we're going to think of x as encoding a function on log m bits. And then we can define an x oracle circuit as simply a circuit which contains gates which compute this function x. Okay, the function x indicated by the string x. And this gate, of course, has log m fanon if x was a string of length m. Okay, we need this definition in order to be able to have an input into this search problem, similarly to how we had an input to the rigid matrix completion problem by providing the first log n rows. So we define complexity as the following search problem. We're given an x of length n, which represents a function on log n bits, and the goal is to find another function on log n inputs, which is not computed by any x oracle circuit, which uses less than some fixed constant times n over log squared n gates. All right, and the existence of such functions, in fact, many, is guaranteed by the simple union bound proof of Shannon. And the log squared n in the denominator there is a technical artifact which comes from the fact that you need log n bits to write down the x oracle circuit gates. The x oracle gates. The details are in the paper. And again, we have that complexity is in PPP. Because one can sort of construct this artificial circuit which computes all functions, all circuits of the size, and then check that none of them compute the function, the candidate function. So this problem is also in PPP. Now, there's something interesting about the previous problems I mentioned. They actually involve a mapping from n-bit strings to m-bit strings, where m is larger than n. And this is different from the PPP problem, in which there simply had to be one more output than input. Here, we're often doubling the output space compared to the input space. So this leads to the following definition. Alpha PPP are those total functions which are reducible to alpha empty, okay? Which is the search problem where given the circuit mapping 2 to the n inputs to 1 plus alpha times 2 to the n outputs, find any empty pigeonhole. In fact, there are many, much more than one, as in PPP. And for simplicity and convenience, we define a PPP to be one PPP. In other words, empty pigeonhole search where the output space is at least twice as big as the input space. And so we have that these two previous natural problems, delta rigid matrix completion and complexity, are in a PPP. So one of the most interesting open problems we pose in our paper is whether complexity and or delta rigid matrix completion are a PPP complete. And sort of as a first step, it would be interesting to see whether they're complete even under NP reductions. And this is interesting because this is a result that's in our paper. I don't mention it here. Under NP reductions, most interesting alpha PPP are equal to each other. If you take any non-negligible alpha, alpha which is greater than 1 over a polynomial, such alpha PPP classes reduce to each other under NP reductions. So another result we show in our paper essentially says that the class APPP might be quite different than PEPP, in which there's just one more output than input, because APPP might be closer to functional NP than may appear at first. Because for non-negligible alpha, the class alpha PPP is in functional P with an NP oracle with polynomial advice. Okay. Actually, the proof for this is very straightforward and is an application of, you guessed it, the union bound. And the proof says something slightly stronger. It says that alpha PPP is a subset of functional ZPP, zero error probabilistic polynomial time with an NP oracle. But in other words, it's close to, in some sense, to FNP. It's an FNP with polynomial advice, and we don't see why, for instance, PPP would be in functional NP with polynomial advice. Now, I'm going to answer a very frequent question that comes up when I talk to people about this. Many people hear this and they start thinking about problems that might be in TF sigma 2 or in PPP, and they say, what about this problem? What about optimization? Given a circuit from n-bit strings to m-bit strings, find a max input, an x such that cx is greater than all other cx prime. Now, this problem is in TF sigma 2. Of course it is, but it's actually already understood in some sense. It's complete for FP with an NP oracle, which is also known as delta 2. And it's simple to figure this out. You can use an NP oracle to just do binary search for this optimum. And this has been understood since the 80s, and it's in Krentel's thesis from 1984. Great. Now, what about higher in the hierarchy? Let's consider TF sigma 3. So let's briefly recall, TF sigma 3 are those total relations where x, y is in the relation if for all A exists B such that M accepts. Are there natural problems at this level of the hierarchy? And the answer is yes. And I will present two of them to you. One of them is shattering, in which large shattered sets are guaranteed by the Sauer-Schella lemma, and kings, a search problem on tournaments kind of digraph where a solution is guaranteed by a simple graph theory argument. So let's take a look. So I'll go over this quickly, but you can pause and take a look at these definitions more carefully if you'd like to review them. Shattering, which is one of the most important definitions in classical learning theory and in VC learning theory, we say that a family of sets F, where the sets are over the same universe, usually the numbers 1 through n, shatters some set S if you can realize any subset T of S. Where by realize, I mean there's some Si in the family that the subset T of S can be realized by taking S intersect with Si from that family. A classic learning theory or set theoretic result, the Sauer-Schella lemma, comes in two flavors. The strong version says that a family of sets F shatters at least cardinality of F sets over the same universe as the sets Si. And the weak form, which is more frequently encountered, basically says that there is a lower bound on the size of a set shattered by the family F. All right, there's a set S, which is shattered by F, whose size is at least D, and we can compute this D. So this, of course, suggests a very natural search problem. Find a shattered set S with size D. And when you think about how you verify shattering, you will see that there's an alternation of quantifiers at play, and this will place it in TF sigma 3. So let's rigorously define the shattering problem. We're given a circuit which implicitly represents a family of sets. All right, it maps k-bit strings to n-bit strings. So in other words, it represents a family of 2 to the k different sets of numbers 1 through n. And we're given D such that by the Sauer-Schella lemma, we're guaranteed the existence of a shattered set of size at least D. And so the search problem is to either find a x1 and x2, two indices such that we get the same set, which means that we don't actually have 2 to the k distinct sets in the family F. So the conditions for the Sauer-Schella lemma aren't satisfied, or find a shattered set S. of size at least d. So when you think about how you verify a possible shattered set S, you need two quantifiers. You check that for every subset T of S, there exists an xi in the family, or an index I such that C of I, that set, realizes this subset T. And so this places shattering in T of sigma 3, on the third level of our total hierarchy. But when you think about this problem, why are we getting a large shattered set? Well, the reason is the strong Sauer-Schell lemma, which says that this family of sets shatters at least cardinality of F sets. So in a sense, there are too many shattered sets. So one of them has to be large because there's so many of them. They can't all be small. So this smells like PPP, polynomial pigeonhole principle, which lives in TFNP, because it smells like collision finding. And in fact, we prove in our paper that shattering lives in oracleized PPP, PPP with a sigma 2 oracle, which is a natural subclass of TF sigma 3. So very briefly, this sort of suggests a line of research where we take problems in TF sigma I and we place them in natural subclasses of TF sigma j for a smaller j, but with oracles. So we sort of find structure between levels of the hierarchy with oracleized versions of these subclasses. So specifically PPP with an O oracle, this is what it means. It's defined as PPP, but where the input circuit instance for which we have to find a collision, that input circuit can use an O oracle. It has O oracle gates. So shattering lives in PPP with sigma 2 oracle gates. So in other words, you can reduce shattering to finding a collision of a polynomial sized circuit where this circuit makes sigma 2 oracle calls. And the idea is to construct a mapping, an explicit mapping, in fact, which uses sigma 2 oracle calls from F to shattered sets. And then with a simple modification, you make large sets collide, and then you're looking for a collision to find a large set. And this is a technical result in our paper, which you can look at if you're interested. And in the remaining few minutes, I'm going to present you with another natural problem that we found in TF sigma 3, the King's problem. So a tournament is a digraph in which exactly one of the following two edges is in the graph, either UV or VU. So you can think of this as a graph representing a tournament, let's say a rock, paper, scissors tournament where everyone has played with everyone, okay? Now a king in a digraph is a vertex which beats, in air quotes, every other vertex, where by beats we mean either it directly beat that vertex, so either K beat U directly, the edge KU is in the graph, or it transitively beats U. It beats a W which beats U. So for every vertex U, it's either beat U or it beats a W which beats that U. Now a very simple graph theory argument tells us that every tournament has a king. And I'll give you the beginning of this argument and you can complete it. Take the tournament and take a vertex which has beat or transitively beat the most vertices, a max, all right? And consider this vertex. It in fact has to be a king, because if it's not a king, that means there's some vertex it either doesn't beat, it neither beats nor transitively beats. But if you think about that other vertex, you'll find that it actually it will beat or transitively beat more vertices than the one you started with. And this is a simple argument, an exercise for you to complete. So this suggests, and it's a non-constructive argument in a sense, given a max, if it's not a max, there exists something it doesn't beat which transitively beats more than it. In a sense, it doesn't tell you how to find the king. So this leads to the definition of a search problem, kings. So given a circuit which implicitly represents a tournament, find a king in this tournament. And this problem lies in TF sigma 3 because a king can be verified by checking that for all other vertices in this graph, in this exponentially sized graph, either the king beats this vertex, or this is where the second quantifier comes in, there exists a W such that the king beats W and then W beats the vertex in question. And at first glance, similarly to how when we thought about shattering, it smelled like PPP in collision finding, this problem seems like an optimization problem. Each vertex in this digraph has a potential or a weight, which is the number of vertices it beats or transitively beats. And so this seems like it should live in in an oracleized version of a specific TFNP subclass called PLS. And roughly speaking, verbally, PLS are those problems which amount to finding a local optimum in a graph. So maybe we would suspect that maybe this problem lives in PLS with a sigma 2 oracle. But the problem is that when you think about how you compute this potential, what circuit would compute the potential of each vertex, you actually need to count how many vertices it beats or transitively beats in the graph. So the oracle would have to allow you to count this. It would have to be sharp P. So it doesn't seem likely that Kings lives in PLS with a sigma 2 oracle. Now, the last two slides are a conclusion. I'll try to sort of summarize everything I've told you about. In short, we have introduced a total polynomial hierarchy and identified natural problems and subclasses in this hierarchy. So TF sigma 2, which is total problems in functional sigma 2, contained the natural empty problem, finding a target in the output space to which no input maps, which leads us to defining PPP. And then we identified other natural problems, such as rigid matrix completion and complexity, for which the output space is actually being doubled. We're looking for an empty output in an output space that at least doubles the input space, which leads us to defining alpha PPP, and in particular APPP. And then we also consider natural problems in TF sigma 3. We find shattering, which has to do with finding large shattered sets. And we find that this actually lives in an oracleized version of PPP. And we also have the graph theoretic Kings problem. Okay, great. And I'll briefly tell you about the open problems that we pose in our paper and future work. So one interesting question we have is, are there other subclasses of TF sigma 2? We know many natural subclasses of TFNP, and which we do not think reduce to one another. So why is there such a dearth in TF sigma 2? And this might have, the answer to this question might have connections to logic, because there are, in logic, one studies sort of generic characterizations of the arguments that lead to subclasses in TFNP. So there are similar generic arguments perhaps for subclasses in TF sigma 2. I've already presented this problem, but one might ask whether complexity and alpha rigid matrix completion are APPP complete. Are they complete even with P to the NP reductions as a starting point? Remote point was another one. Is this one APPP complete for large D? What about if you restrict this problem to only considering linear codes? Another big question is the classification of Kings. So we actually have some recent results after we published this. We actually identified a second natural subclass of TF sigma 2, which we call PPM, for polynomial post-set maximization, which has to do with finding maximal elements in an implicit post set represented by a circuit. And a finite post set might have many maximal elements, and this turns out to not be the same thing as optimization, which I presented in that FAQ slide earlier. So we don't think right now that PPM is the same thing as PPP. So this might be a second natural subclass of TF sigma 2. And we find the reason we define this is because Kings lives in PPM with an NP oracle. So this, put simply, sort of exhibits some structural connection between the second and third levels of the total hierarchy. And one can try to look for other natural problems in other TF sigma I, perhaps at higher levels of the hierarchy, and there are many structural questions that we also pose in the paper that have to do with collapse of this hierarchy and other connections between these classes. I should mention, this isn't in the slide, but there are many cryptographic questions that could be asked about these questions. Can we connect hardness assumptions on these subclasses or TF sigma 2 to crypto primitives or such things. So I hope this was interesting. And if you'd like to learn more, please take a look at our paper and please get in touch with us if you have any thoughts. Thank you.